Welcome to the Late Lab. I'm very glad you found your way here tonight. Before we settle in, tell me where in the world you're listening from. Maybe you're already tucked into bed, stretched out on the sofa, travelling somewhere late at night, or simply enjoying a quiet few minutes while everything around you slows down. Wherever you happen to be, get comfortable, let the day fade into the background, and make yourself at home for a little while. And if these slow journeys through science are something you enjoy, you can always leave a like and subscribe to help the Late Lab keep growing. If you're already here regularly, thank you for coming back. It genuinely means a great deal. Tonight, we're looking at something that sounds as though a quantum particle has discovered how to cheat. Imagine rolling a ball towards a hill without giving it enough energy to reach the top. There should be only one possible outcome. It rolls partway up, stops, and comes back down. Yet in the quantum world, place a particle in an equivalent situation, and every so often, it can be detected on the other side. No secret doorway, no sudden burst of extra energy, and, unfortunately, no useful instructions for walking through your bedroom wall. So settle in and let's begin. Why can a quantum particle pass through a barrier it should never be able to cross? The easiest way to understand why quantum tunneling feels so strange is to begin with a world in which it cannot happen at all. Imagine a ball rolling towards a hill. The ball starts with a certain amount of motion, carrying what physicists call kinetic energy. As it climbs, it slows down. Some of that kinetic energy is being converted into gravitational potential energy because the ball is moving higher in Earth's gravitational field. If the ball begins with enough energy, it can reach the summit and continue down the other side. But if it begins too slowly, there is a height it simply cannot pass. The ball rises, slows, reaches a moment when its upward motion stops completely, and then rolls backwards. Nothing mysterious has happened. In classical physics, this is exactly what should occur. The reason comes from conservation of energy, one of the most fundamental principles in physics. Energy can move between different forms, but in an isolated system it does not simply appear from nowhere. The ball cannot suddenly gain the extra energy it needs simply because the top of the hill happens to be inconveniently high. Its total energy is divided between kinetic energy, associated with motion, and potential energy, associated with its position within some physical interaction. As the potential energy rises, the amount available as kinetic energy falls. Eventually, if the hill is high enough, the kinetic energy reaches zero. That location is known as a classical turning point. Beyond it, continuing up the hill would require the ball to possess more potential energy than its total energy allows. There would be nothing left to convert into that additional potential energy. Classical mechanics, therefore, gives a very simple answer. The ball cannot continue. The same reasoning works in many situations. A pendulum swings upwards, slowing as it climbs. Unless something gives it additional energy, it cannot swing higher than the height permitted by the energy it started with. A spacecraft moving away from a planet loses speed as it climbs through the planet's gravitational field. If it does not have sufficient energy to escape, gravity eventually brings it back. The details differ, but the basic logic remains the same. There are regions that an object can reach, and regions that its available energy makes inaccessible. Physicists often describe this using a potential energy landscape. Instead of imagining a literal hill, we can imagine a graph in which different positions correspond to different amounts of potential energy. A raised section becomes an energy barrier. For a classical particle approaching such a barrier, the rule seems uncompromising. If the particle has more energy than the barrier requires, it can cross. If it has less, it cannot. There is no probability involved. A classical particle does not have a tiny chance of succeeding if it tries repeatedly. It does not occasionally get lucky. If its total energy lies below the top of the barrier, classical mechanics predicts that its probability of appearing on the far side is exactly zero. That certainty is important, because it shows why quantum tunneling is more than merely an unusual form of motion. Classical particles are also imagined as occupying definite positions and following continuous trajectories through space. If you know where a ball begins and understand the forces acting upon it, classical mechanics describes a continuous path from one location to another. The ball cannot be on the left side of a hill, fail to climb over it, and later appear on the right side without passing through all the positions in between. There is simply no place in the classical picture for that to happen. Now shrink the problem down to the scale of an electron or another quantum particle. Suppose the particle approaches an energy barrier whose height exceeds the particle's energy. Classical physics gives exactly the same verdict as before. The particle must be reflected. It should never emerge on the opposite side. But quantum mechanics gives a different answer. It still predicts that reflection can occur. In many situations, reflection is overwhelmingly likely, yet it also predicts something classical physics completely forbids. There can be a non-zero probability of transmission. Prepare enough particles in the same way and send them towards the same barrier, and some can be detected beyond it, even though none possesses enough energy to cross the barrier in the ordinary classical sense. This is quantum tunneling. The particle has not secretly received a push. The energy barrier has not briefly vanished. Conservation of energy has not been casually ignored while nature hoped nobody was paying attention. Instead, the difference comes from something more fundamental. The classical picture itself is no longer sufficient. At microscopic scales, particles cannot always be treated as tiny solid objects travelling along perfectly defined paths. Quantum mechanics replaces that familiar description with a very different one, and once that change is made, the apparently impossible journey through a barrier begins to look less like a violation of the rules. It becomes a consequence of the rules themselves. For a long time, the most natural way to imagine matter was as a collection of tiny objects. An electron, in this picture, would simply be an extremely small particle moving from one place to another. It might be difficult to see, unimaginably light, and governed by forces quite unlike the ones we experience directly, but it would still behave like a little object. That comfortable picture began to unravel in the early 20th century. One of the most important steps came from the French physicist Louis-Victor de Broglie. In 1924, de Broglie proposed something remarkable. If light, which had long been understood as a wave, could sometimes behave like a particle, perhaps particles of matter could also behave like waves. It was a bold reversal of the problem. Only a few years earlier, Albert Einstein had helped establish that light could exchange energy in discrete packets, later called photons. Light seemed capable of displaying both wave-like and particle-like behaviour, depending on how it was observed. De Broglie wondered whether nature might be more symmetrical than anyone had expected. Perhaps matter had the same strange dual character. He proposed that a moving particle has an associated wavelength determined by its momentum. The relationship can be expressed in words as the wavelength equals Planck's constant divided by the particle's momentum. This wavelength is now known as the de Broglie wavelength. For large everyday objects, it is absurdly small. A tennis ball moving across a court has a de Broglie wavelength so tiny that its wave properties are completely invisible in ordinary life. But for something as light as an electron, the wavelength can become comparable with the spacing between atoms in a crystal. And that made the idea testable. If electrons really possessed wave properties, they should be capable of producing diffraction. Diffraction is one of the characteristic behaviors of waves. Water waves spread after passing through an opening. Sound bends around obstacles. Light passing through sufficiently narrow structures produces patterns of bright and dark regions because different parts of the wave combine and interfere. A collection of ordinary classical particles would not naturally produce the same pattern. This provided an elegant experimental question. Send electrons towards a carefully arranged structure and see whether they behave like tiny projectiles or like waves. In the 1920s, Clinton Joseph Davison and Lester Halbert Germer were studying electrons scattering from a nickel crystal at Bell Telephone Laboratories in the United States. Their experiment was not originally designed as a grand demonstration of matter waves, yet the nickel crystal provided something extremely useful. Its atoms were arranged in a regular repeating structure. That regular spacing acted rather like a natural diffraction grating. When Davison and Germer directed electrons at the crystal and measured how strongly they scattered in different directions, they discovered distinct peaks at particular angles. The electrons were not simply bouncing away in the pattern expected from tiny classical particles striking a surface. They were producing diffraction. The measured pattern agreed with the wavelength predicted by Louis-Victor de Broglie's relationship. Matter really did possess wave-like behavior. This was not merely a curious detail about electrons. It changed the basic language needed to describe the microscopic world. An electron could no longer be understood completely as a tiny solid bead with a definite position and a definite path at every moment. That picture could still be useful in certain circumstances, but it was not fundamental enough to account for what experiments were showing. At the same time, calling an electron a wave can also create the wrong impression. A matter wave is not simply a faint physical ripple spreading through space like a wave travelling across a pond. There is no tiny sheet of electron material wobbling up and down as it travels. The quantum description is more abstract. What spreads through space is a quantum state, described mathematically by something called a wave function. That state carries information about the possible results of measurements and can display genuinely wave-like features such as interference and diffraction. The distinction matters because ordinary waves and quantum waves are not identical things. A water wave can be divided into pieces of moving water. A sound wave consists of variations in pressure travelling through a material such as air. A quantum matter wave does not require a comparable physical medium. Yet one particularly important property remains. Waves are extended. They do not have to occupy only one sharply defined point. A wave can stretch across a region, interact with several possible paths, and respond to boundaries in ways that a classical point particle cannot. That simple fact begins to change how we should think about barriers. Imagine once again an electron approaching a region that classical physics says it cannot enter. If we insist on picturing the electron only as a tiny object travelling along a single path, the problem seems impossible. It reaches the barrier, lacks enough energy to cross, and must turn around. But the quantum state associated with that electron is not necessarily confined to one mathematical point. It can extend across space, and when an extended quantum state encounters a barrier, the question is no longer merely whether a tiny object has enough energy to climb over it. The question becomes what happens to the wave function when it reaches the boundary. Some of that quantum state can be reflected, but under the right circumstances, the state can also extend into a region that classical physics would declare forbidden. This is the first real clue to quantum tunneling. The particle does not succeed because it has somehow become stronger than the barrier. The deeper reason is that the particle was never adequately described as a tiny classical object in the first place. Once matter began to reveal wave-like behavior, physicists needed a new mathematical language capable of describing it properly. That language emerged most clearly through the work of Erwin Rudolf Joseph Alexander Schrödinger. In the mid-1920s, Schrödinger developed what became known as wave mechanics, a formulation of quantum mechanics built around a mathematical object called the wave function. Instead of describing a particle only by giving it a precise position and a definite trajectory, the wave function describes the quantum state of the system. That is a very different kind of description. In classical mechanics, imagine throwing a ball across a room. At every moment, at least in principle, the ball has a particular position and a particular velocity. If those quantities are known accurately enough, along with the forces acting on the ball, its future trajectory can be calculated. There is a continuous path connecting where it started with where it eventually arrives. Quantum mechanics does not generally describe an electron in quite the same way. Rather than assigning the electron one ordinary path through space before a measurement is made, the theory can describe a state spread across many possible positions. The wave function contains what physicists call probability amplitudes. That phrase is important because the wave function itself should not simply be imagined as a cloud of electron material floating through space. It is not quite like spreading a spoonful of smoke through a room and saying that some fraction of the electron is physically sitting in each corner. The connection between the wave function and measurable probabilities was clarified by Max Born. In 1926, Born proposed that the wave function should be interpreted probabilistically. In simplified terms, the squared magnitude of the wave function at a particular location determines the probability density for detecting the particle there. Probability density is slightly different from ordinary probability. For a particle moving along a line, it tells us how likely a detection is within a small region around a particular position. Where the probability density is large, detection is relatively likely. Where it is small, detection is less likely. Where it is exactly zero, that particular measurement outcome cannot occur according to the state being described. Before the measurement, however, quantum mechanics does not normally require us to imagine that the particle was secretly sitting at one definite location all along, merely waiting for us to discover it. The wave function can extend across a broad region. That is one of the reasons quantum mechanics feels so unfamiliar. A classical trajectory resembles a thin line through space. The object is here, then slightly farther along, then farther along again. A quantum state can instead assign probability amplitudes to many different positions at once. This does not mean that one electron has literally been sliced into hundreds of smaller electrons and scattered around the laboratory. It means that a single quantum state can contain multiple possible measurement outcomes. This is part of what physicists mean by superposition. A superposition is a state formed from a combination of different possible quantum states. An electron may, for example, be described by a wave function containing amplitude associated with several different positions. When the position is measured, one location is detected. But before that measurement, the mathematical state need not behave as though only that eventual result existed. The strange part is that these amplitudes can also interfere with one another. They can reinforce or partially cancel in much the same mathematical way that ordinary waves can interfere, although the physical interpretation is fundamentally quantum mechanical. This makes the wave function far more than a convenient map of our ignorance. Its structure affects experimentally observable outcomes, and this becomes essential when a particle encounters a barrier. If we picture an electron as nothing more than a tiny bead travelling along a single hidden path, then tunneling becomes almost impossible to understand. The bead reaches the barrier. It does not have enough energy to cross. So perhaps, one might imagine, it finds an invisible crack. Or perhaps it somehow jumps instantaneously from one side to the other. Neither picture captures what the quantum theory is actually saying. The correct starting point is the entire wave function. As that wave function evolves, it responds to the potential energy landscape surrounding the particle. When it reaches a barrier, the wave function does not necessarily end abruptly at the exact position where classical motion would become forbidden. Its behavior changes, but it can continue into the barrier. Under suitable conditions, some of the quantum amplitude can even extend all the way through to the region beyond it. That is why tunneling is not really the story of a tiny object making a daring escape through a microscopic hole. It is the story of a quantum state evolving according to rules that have no exact classical equivalent. The particle is eventually detected at a particular place. That detection is perfectly real. But the description leading to that detection is not necessarily a miniature version of an ordinary object travelling along a familiar path. And once the classical trajectory is replaced by the wave function, the barrier begins to look very different. It is no longer a place where the quantum description simply has to stop. The wave function gives us a new way to describe a quantum particle, but by itself it does not tell us how that description changes with time or responds to the environment around it. For that, quantum mechanics uses the Schrödinger equation. Developed by Erwin Rudolf Joseph Alexander Schrödinger in the 1920s, the Schrödinger equation plays a role in quantum mechanics somewhat similar to the role that Newton's laws play in classical mechanics. Given a quantum state and a description of the forces or potential energies acting on it, the equation tells us how the wave function evolves. For particles moving slowly enough that relativistic effects can be ignored. It is one of the central equations of quantum theory, and it is exactly what we need if we want to understand a barrier. Imagine an electron moving from left to right through an otherwise empty region. Ahead of it sits a very simple obstacle, not a brick wall or a sheet of metal, but an idealized potential energy barrier. Physicists often imagine this barrier as perfectly rectangular. For some distance, the potential energy is low. Then, at one particular location, it rises suddenly to a higher value. It remains high across a finite width, and then drops back down again. This is deliberately simple. Real barriers are often more complicated, with smoother shapes and interactions that vary continuously. But the rectangular barrier makes the basic physics much easier to see. Now suppose the incoming electron has less total energy than the height of that barrier. Classically, the answer is immediate. The electron cannot pass. It reaches the barrier and reflects. Quantum mechanics asks a slightly different question. What form of wave function satisfies the Schrödinger equation in every region of this potential? There are three regions to consider: before the barrier, inside the barrier, and after the barrier. Before the barrier, the wave function can contain an incoming component representing motion towards the obstacle, but it can also contain a reflected component representing motion back in the opposite direction. These components behave like waves, and together they describe the quantum possibilities available on the incoming side. If the barrier were absent, the incoming wave could simply continue. But once the potential rises, the equation governing the wave function changes because the potential energy has changed. This is the point where classical and quantum reasoning begin to separate dramatically. Classical mechanics says that if the potential energy rises above the particle's total energy, there is no physically allowed forward motion through that region. The particle would require negative kinetic energy, which has no meaning in ordinary classical mechanics. So the classical trajectory stops at the turning point. The Schrödinger equation does not stop. It still has valid mathematical solutions inside the region where classical motion is forbidden. Those solutions behave differently from the freely travelling waves outside the barrier, but they do exist. That difference is crucial. The barrier does not make the wave function vanish the instant it begins. Instead, the form of the wave function changes. To understand why, it helps to think about what happens at the boundary between two regions. A physically acceptable wave function cannot normally make an arbitrary jump from one value to a completely unrelated value simply because the potential has changed. For an ordinary finite potential barrier, the wave function must join smoothly across the boundary. Its spatial behavior must also match in the appropriate way. In more formal language, the wave function and its first spatial derivative are continuous across the boundary for the usual finite barrier with a finite potential step. That requirement may sound like a small mathematical technicality, but it has enormous physical consequences. Suppose the wave function has some non-zero value immediately before the barrier. If the barrier itself is finite, the wave function cannot simply fall vertically to zero at the boundary without violating the required matching conditions. The quantum state must continue into the barrier. It may change character very quickly once inside, but it does not disappear. This is the beginning of tunneling. The same matching conditions must also be applied at the far side of the barrier. So the Schrödinger equation has to produce a complete solution that works before the barrier, within it and beyond it. The three pieces are not independent stories. They must fit together into one consistent quantum state. That is very different from imagining an electron arriving at a wall and deciding whether to bounce or somehow squeeze through. There is no little decision being made. The entire wave function responds to the potential landscape according to the Schrödinger equation. Before the barrier, part of the mathematical solution corresponds to reflection. Inside the barrier, another form of solution appears, and if some amplitude survives across the width of the barrier, the solution on the far side can contain a transmitted component. This is why the classical phrase forbidden region can be slightly misleading. It is classically forbidden. It does not mean that quantum mechanics refuses to describe anything there. Quite the opposite. Quantum mechanics gives the region a perfectly well-defined wave function. The real surprise is that the mathematics allows that wave function to reach into a place where a classical particle could never travel. And once it reaches into the barrier, the possibility appears that it may reach beyond it as well. The wall has not disappeared. The particle has not acquired extra energy. The rules have simply changed because the object approaching the barrier is not governed by a classical trajectory. It is governed by a wave function. And the Schrödinger equation refuses to let that wave function end abruptly, just because classical intuition would prefer a cleaner answer. Once the wave function enters the classically forbidden region, something very specific happens to its mathematical form. Outside the barrier, where the particle's total energy is greater than the local potential energy, the wave function typically behaves in an oscillating way. In simple cases, it resembles a travelling wave with a repeating pattern that corresponds to propagation through space. Inside the barrier, that changes. If the potential energy is greater than the particle's total energy, the Schrödinger equation no longer produces the same kind of freely oscillating solution. Instead, the wave function takes on an exponentially changing form. For the part relevant to ordinary tunneling, that usually means exponential decay. The farther the wave function extends into the barrier, the smaller its amplitude becomes. This is sometimes described as an evanescent quantum wave. The word evanescent simply means fading away. Similar mathematical behavior appears in other areas of wave physics. For example, certain electromagnetic fields can extend a short distance into regions where ordinary propagation does not occur. But in quantum mechanics, the meaning is tied to the wave function and its probability amplitudes rather than to a classical electromagnetic wave carrying energy through space in the usual way. So it is important not to imagine the quantum particle as a tiny ripple physically crawling through the barrier. The wave function inside the barrier is not behaving like an ordinary travelling wave. Its amplitude is decaying. Suppose the barrier begins at some particular position. At that boundary, the wave function has a non-zero value. Because the barrier is finite, the matching conditions of the Schrödinger equation require the wave function to continue into it. A short distance inside, the amplitude is smaller. A little farther in, smaller again. The decline is exponential, which means the reduction becomes extremely strong as distance increases. This is why barrier thickness matters so much. If the barrier is very wide, the amplitude can become so tiny before reaching the far side that the probability of transmission is effectively negligible. But if the barrier is thin enough, the situation is different. The wave function may decay substantially and still retain a small non-zero amplitude when it reaches the second boundary. And this is the crucial point. The wave function does not need to remain large, it only needs not to be exactly zero. At the far edge of the barrier, the matching conditions apply again. The decaying wave function inside must connect consistently to a solution in the region beyond the barrier. If the potential energy drops back below the particle's total energy, the wave function can once again take on an oscillating form. That oscillating component on the far side corresponds to transmission. In other words, the quantum state has acquired a component associated with the particle being found beyond the barrier. This is not a statement that the particle has climbed over the barrier in the classical sense. It is not even quite a statement that it has travelled through the barrier in the familiar everyday sense of following a visible path from one side to the other. What the mathematics tells us is that the complete quantum state includes a non-zero amplitude on the far side. When a position measurement is later made, there is therefore a non-zero probability of detecting the particle there. The distinction between amplitude and probability is worth keeping clear. The wave function contains probability amplitudes. These amplitudes can be positive, negative, or even complex quantities in the mathematical sense, and they can interfere with one another. The measurable probability is related to the squared magnitude of the relevant amplitude. So if the wave function amplitude becomes very small inside the barrier, the corresponding transmission probability becomes smaller still. This helps explain why tunneling can range from fairly noticeable to essentially impossible depending on the circumstances. A barrier that is only slightly higher than the particle's energy and extremely narrow may allow a meaningful tunneling probability. Increase the width, raise the barrier, or use a much heavier particle, and that probability can collapse by enormous factors. The exponential nature of the process is unforgiving. This also shows why there is an important difference between a finite barrier and certain idealized barriers. If a barrier is infinitely wide, there is no far boundary for the decaying wave function to reach. It simply continues decreasing without ever emerging into another allowed region. Likewise, an idealized infinitely high barrier imposes much stricter conditions. In the simplest textbook treatment, the wave function is forced to vanish at the boundary, eliminating the ordinary transmission that occurs through a finite barrier. Real physical barriers are not usually infinite in either height or width. They have finite dimensions and finite energy scales. That leaves room for the wave function to penetrate them. And nothing extra has to be added to quantum mechanics to make this happen. There is no special tunneling force. There is no hidden interaction that pushes the particle through. There is no moment when the barrier becomes temporarily weaker. The effect comes directly from the way the Schrödinger equation behaves when a quantum state encounters a region where the potential energy exceeds the particle's total energy. Classical physics says the particle cannot enter that region because a classical trajectory would require impossible negative kinetic energy. Quantum mechanics asks a different question. What wave function satisfies the equation across the entire potential landscape? The answer is that the wave function can extend into the forbidden region, fade exponentially, and, if the barrier is narrow enough, retain enough amplitude to connect with the transmitted state on the other side. That tiny surviving amplitude is all tunneling needs. The barrier is still there. The particle still has less energy than the barrier height. But the quantum state never had to obey the classical rule that the wave function must stop where the classical trajectory stops. And so the region that looked absolutely forbidden turns out to be only classically forbidden. When a quantum particle reaches a barrier, there are usually two broad possibilities. It can be reflected back towards the region it came from, or it can be transmitted through to the other side. Quantum mechanics assigns a probability to each outcome. The reflection probability tells us how likely the particle is to be found back on the original side. The transmission probability tells us how likely it is to be detected beyond the barrier. For a simple barrier with no absorption or other complications, those probabilities together account for the possible outcomes. If transmission becomes more likely, reflection becomes less likely, and vice versa. What quantum mechanics generally does not allow us to predict is the result of one individual event with complete certainty. Suppose we prepare a single electron in a particular state and send it towards a barrier. Perhaps the theory predicts a transmission probability of 1 in 10. That does not mean 1/10 of the electron squeezes through. The electron is eventually detected as a whole, nor does it mean that every 10th electron must tunnel in some perfectly organized sequence. One particle might reflect, the next might tunnel, several more might reflect, another might pass through. The individual results appear probabilistic. But prepare thousands or millions of electrons in the same way, and the overall proportions become remarkably stable. Roughly the predicted fraction will be transmitted, while the remainder will be reflected. Quantum uncertainty at the level of individual events produces highly predictable statistics when many events are considered together. The interesting question, then, is what determines the transmission probability. One of the most important factors is the width of the barrier. Because the wave function decays exponentially inside a classically forbidden region, adding even a modest amount of extra width can make an enormous difference. Imagine that the amplitude decreases by some fixed factor over a certain microscopic distance. If the barrier becomes twice as wide, that reduction does not merely become twice as severe. The wave function continues decaying across the additional distance, multiplying the suppression again. The transmission probability can therefore fall extremely quickly. This is why tunneling often matters across distances measured in fractions of a nanometer or a few nanometers, yet becomes negligible when the same kind of barrier is made substantially thicker. At quantum scales, a tiny change in distance can be the difference between a measurable current and almost no current at all. Barrier height matters too. More precisely, what matters strongly is the difference between the potential energy of the barrier and the energy of the incoming particle. If the particle's energy lies only slightly below the top of the barrier, the wave function decays relatively slowly inside the forbidden region. The particle therefore has a better chance of being transmitted. If its energy lies far below the barrier height, the decay becomes more rapid, and tunneling is strongly suppressed. so a particle approaching what might be called the top of the hill has a greater chance of tunneling than one sitting far below it. It still does not possess enough energy to cross classically, but the quantum probability can be much larger. Mass introduces another powerful effect. Under otherwise similar conditions, heavier particles tend to tunnel less readily than lighter ones. The mathematical rate at which the wave function decays inside the barrier depends partly on the particle's mass. A larger mass generally produces a faster decay, and therefore a smaller transmitted amplitude. This helps explain why electrons are especially well suited to tunneling. An electron has a mass of roughly 9 times 10 to the minus 31 kilograms, extraordinarily small on everyday scales. Protons are around 1800 times heavier than electrons, so proton tunneling is usually more strongly suppressed under comparable conditions, although it remains important in processes such as nuclear reactions and some chemical reactions. Move all the way up to an everyday object, and the situation becomes almost absurd. A grain of sand contains an enormous number of particles and has a mass vastly greater than an electron. A person is more extreme still. The tunneling probability for an entire macroscopic object through an ordinary wall is not merely small in the casual sense. For realistic conditions, it is so fantastically suppressed that treating the probability as effectively zero is entirely reasonable. Quantum mechanics has not stopped working. The numbers have simply become merciless. Physicists have developed useful methods for estimating tunneling probabilities without solving every quantum problem exactly. One particularly important approach is the Wenzel-Kramers-Brillouin approximation, named after Gregor Wenzel, Hendrik Anthony Kramers, and Lon Brillouin. This is a semi-classical approximation, meaning that it uses ideas that sit between fully classical intuition and a complete quantum solution. It is especially useful when the potential energy changes relatively smoothly with position. The method shows clearly why tunneling depends exponentially on quantities such as particle mass, the shape and height of the barrier, and the width of the forbidden region. That exponential dependence is the real reason tunneling can feel so selective. Change a barrier slightly, and the outcome can change enormously. Move two conducting surfaces just a little farther apart, and an electron tunneling current can collapse. Bring them slightly closer, and the current can rise dramatically. Increase a particle's energy towards the barrier height, and transmission can become far more likely. Use a heavier particle, and the probability may fall sharply. There is therefore no single answer to whether a particle will tunnel. The question always depends on the particular quantum system. What particle is involved? How massive is it? How wide is the barrier? How high is the barrier compared with the particle's energy? And what shape does that barrier have? Quantum tunneling is probabilistic, but it is not arbitrary. The individual event may surprise us, the statistics do not. Once the properties of the particle and barrier are known, quantum mechanics can predict the transmission and reflection probabilities with extraordinary precision. And those probabilities reveal something rather elegant. A barrier does not simply divide the quantum world into possible and impossible. Instead, it creates a spectrum of likelihoods. Some particles are almost certain to reflect. Some have a noticeable chance of passing through. And under the right conditions, what classical physics declared absolutely forbidden becomes merely unlikely. One of the most persistent explanations of quantum tunneling is also one of the most misleading. You may have heard that a particle gets through a barrier by temporarily borrowing some extra energy from the universe. The idea usually goes something like this. The particle does not have enough energy to cross the barrier, but quantum mechanics allows it to borrow the missing amount for a very short time, climb over the obstacle, and then pay the energy back before anyone notices. It is a neat story. It is also not how ordinary quantum tunneling works. A particle does not need to acquire enough energy to rise above the barrier at any stage in the standard quantum description. Consider a particle approaching a static potential barrier. Its energy is lower than the barrier height. Before the interaction, the particle has some definite energy. After tunneling, if it is detected on the far side, it can still have that same energy. Nothing has been borrowed. Nothing has been added. The particle has not briefly become more energetic than it was before. Instead, the wave function associated with the particle extends into the classically forbidden region and can retain a non-zero amplitude beyond the barrier. The transmission occurs because of the structure of the quantum state, not because the particle temporarily finds extra energy. This distinction matters because energy conservation remains fully respected. For a time-independent barrier, the Schrödinger equation allows stationary energy states in which the energy of the instant and transmitted parts of the wave function is the same. The barrier changes the spatial behavior of the wave function. It does not have to change the total energy. So where did the idea of borrowed energy come from? Much of the confusion comes from the uncertainty principle associated with Werner Karl Heisenberg. The best-known version is the position-momentum uncertainty principle. It tells us that certain pairs of physical quantities cannot both be prepared with arbitrarily precise values at the same time. Position and momentum are the classic example. Roughly speaking, a quantum state that is very tightly localized in position must contain a broader range of possible momenta, while a state with extremely well-defined momentum must be spread more widely in position. This is not simply a statement that our measuring instruments are clumsy. It is built into the mathematical structure of quantum mechanics. There is also an energy-time uncertainty relationship, and this is where explanations can become dangerously casual. It is sometimes interpreted as saying that energy conservation can be violated as long as the violation lasts for only a sufficiently short time. That interpretation is not generally correct. Time does not enter ordinary quantum mechanics in exactly the same way as position, and the energy-time uncertainty relationship has several precise meanings depending on the physical situation being discussed. It can describe relationships between the spread in energy of a state and characteristic times over which that state changes. It can also appear in discussions of unstable states and spectral line widths. What it does not provide is a universal permission slip allowing particles to temporarily break conservation of energy. The universe does not operate a microscopic lending service. The reason tunneling sounds as though extra energy should be needed is that we are still tempted to imagine the particle following a classical path through the barrier. In classical mechanics, the total energy can be divided into kinetic energy and potential energy. If the potential energy rises above the total energy available to the particle, then maintaining the classical relationship would require the kinetic energy to become negative. For an ordinary classical particle, that cannot happen. The point at which the kinetic energy would reach zero becomes a turning point, and the particle reverses direction. That is why the interior of the barrier is called a classically forbidden region. The phrase can sound stronger than it really is. It does not mean that quantum mechanics declares the region physically non-existent. It does not mean that the wave function is banned from entering. It means that no ordinary classical trajectory with that total energy can pass through the region. Quantum mechanics uses a different description. Inside the barrier, the wave function changes from an oscillating form into an exponentially varying form. The probability amplitude becomes smaller with distance, but for a finite barrier it need not become exactly zero. There is therefore no requirement for the particle to climb over the barrier. The quantum state can extend through it. This is the real conceptual shift. Tunneling is not a failure of conservation of energy. It is a failure of the classical trajectory picture to describe the quantum system correctly. A similar misunderstanding sometimes appears in explanations involving virtual particles. Virtual particles are mathematical features that arise in certain calculations in quantum field theory. They can be extremely useful within perturbation theory, where interactions are represented using particular mathematical techniques. But they should not be imagined as tiny hidden particles constantly appearing from nowhere and handing energy to anything that happens to need it. Ordinary tunneling through a simple static barrier does not require virtual particles to carry the real particle across. Nor does it require random vacuum fluctuations to give the particle a lucky shove. Quantum fields and vacuum phenomena are real and important parts of modern physics, but adding them to a simple tunneling explanation usually makes the picture less accurate rather than more complete. The basic mechanism is already contained in quantum mechanics. Prepare a particle with energy below a finite barrier. Let its wave function evolve according to the Schrödinger equation. The wave function penetrates the forbidden region, decays there, and may retain a non-zero amplitude beyond the far boundary. A later measurement can then find the particle on the opposite side. The transmitted particle has not cheated. It has not paid back a secret energy debt. It has simply behaved according to rules that never required it to follow the classical route in the first place. The barrier is higher than the particle's energy. That remains true before, during, and after the tunneling process. What changes is not the amount of energy available. What changes is our understanding of what a quantum particle is allowed to do. Once tunneling is described in terms of a wave function extending through a forbidden region, another question almost immediately appears. What path does the particle actually take? It is a very natural question, because almost everything in everyday life reaches its destination by travelling continuously through the space between its starting point and its ending point. A car moves along a road. A stone follows an arc through the air. A planet traces a continuous orbit around a star. If we find an object on one side of a barrier and later detect it on the other, our instinct is to imagine some hidden route connecting those two observations. Quantum mechanics makes that instinct much harder to satisfy. Suppose an electron is prepared on the left side of a finite potential barrier. Its quantum state evolves, the wave function extends into the barrier, and after some time the electron is detected on the right. The experimental facts are clear. There was an incident quantum state approaching the barrier. There was some probability of reflection. There was some probability of transmission. And in a successful tunneling event, a detector registered the electron beyond the barrier. What ordinary quantum mechanics does not necessarily provide is a classical movie showing the electron occupying one definite intermediate position after another as it passes through. That distinction is important. The wave function can have non-zero amplitude inside the barrier. This means the quantum state genuinely includes the forbidden region in its mathematical description. But that statement is not identical to saying that the electron secretly followed a tiny continuous trajectory through every point inside the barrier. The first statement is part of the standard quantum formalism. The second adds a particular picture of what the particle was doing when nobody measured it. And quantum mechanics is famously cautious about such pictures. A measurement before the barrier can establish that an electron has been prepared in an incoming state. A detector after the barrier can establish that an electron has been transmitted. but those observations alone do not reconstruct a classical path between them. Trying to measure the electron repeatedly inside the barrier would also change the physical situation. Quantum measurements are interactions with the system, and sufficiently invasive measurements can alter the state whose undisturbed behavior we were attempting to understand. This leads into a broader issue known as the measurement problem. Quantum theory provides extraordinarily successful rules for predicting measurement outcomes. A wave function evolves according to the Schrödinger equation, and measurement probabilities are obtained from that state. What remains conceptually difficult is explaining exactly how the mathematical quantum state relates to the single definite outcomes we actually observe. Different interpretations of quantum mechanics offer different answers. Within the broad family often called the Copenhagen interpretation, associated historically with figures including Niels Henrik David Bohr and Werner Karl Heisenberg, the emphasis is generally placed on the predictions available from the quantum state and on the outcomes of measurements rather than on assigning an unseen classical trajectory to the particle between observations. From that perspective, asking which exact path an unmeasured tunneling particle followed may simply be demanding a kind of description that the theory does not supply. Another approach gives a very different picture. The de Broglie-Bohm pilot wave formulation traces its roots to Louis Victor de Broglie and was developed in a systematic form by David Joseph Bohm in the 20th century. In this formulation, particles do possess definite positions and trajectories. The wave function still evolves, but it also guides the particle according to an additional dynamical rule. A tunneling event can therefore be described in terms of an actual particle trajectory influenced by the guiding quantum wave. That sounds much closer to classical intuition, although the resulting motion remains thoroughly non-classical. The important point is that these interpretations can tell different stories about what happens between preparation and detection, while still reproducing the same standard experimental predictions for ordinary tunneling situations. One interpretation may avoid assigning a definite intermediate path. Another may insist that a definite trajectory exists. The measurable transmission probability can nevertheless come out the same. This is why tunneling itself should not be confused with the debate over quantum interpretation. We do not need to settle the deepest philosophical questions in quantum mechanics before calculating whether an electron can pass through a thin barrier. The Schrödinger equation gives the evolving state. The form of the potential determines how that state behaves. The wave function penetrates the classically forbidden region. Boundary conditions connect the solutions on each side. And from the resulting state, physicists calculate reflection and transmission probabilities. Those predictions can then be tested experimentally. Whether someone prefers a Copenhagen-style interpretation, a de Broglie-Bohm description, or another interpretation does not change the observed fact that tunneling occurs. There is also a subtle danger in asking where the particle was at every instant. The question assumes that position must always possess the same kind of definite value that it does in classical physics, but quantum mechanics does not automatically grant that assumption. A quantum state can be spread over a region, and different possible positions can contribute simultaneously to its evolution. Only when a position measurement is actually performed do we obtain one particular detected location. So the safest statement is not that the particle definitely sneaks through the barrier along some invisible microscopic tunnel. Nor is it necessary to say that it literally disappears and instantly materializes elsewhere. Both images can import more classical detail than the experiment establishes. What we can say with confidence is simpler. A quantum state can begin predominantly on one side of a finite barrier. That state can evolve with non-zero amplitude inside the barrier and beyond it, and later, A measurement can detect the particle on the opposite side with a probability predicted by quantum mechanics. The journey between those observations is where classical language begins to lose its grip. The particle arrives. The probability can be calculated. The experiment can be repeated. But the demand for one ordinary hidden path through the barrier may say more about how we expect objects to behave than about what quantum theory requires. Quantum tunneling might sound like the sort of effect that belongs only in carefully controlled experiments, with delicate equipment and particles being fired at artificial barriers. But nature had been using it long before anyone knew what tunneling was. One of the earliest places where the phenomenon revealed itself was radioactive decay. Certain unstable atomic nuclei spontaneously emit what is known as an alpha particle. An alpha particle is made from 2 protons and 2 neutrons, the same combination found in the nucleus of a helium atom. Inside an unstable nucleus, this cluster can exist in a region where the strong nuclear interaction helps hold nuclear matter together. The strong nuclear interaction is extremely powerful over very short distances, but it fades rapidly as the separation between particles increases. Once an alpha particle begins moving away from the nucleus, another interaction becomes increasingly important. Both the alpha particle and the remaining nucleus carry positive electric charge. Positive charges repel one another through the electromagnetic interaction. This creates an effective potential energy barrier surrounding the nucleus. And that produces a problem. Experiments showed that alpha particles could emerge from radioactive nuclei with energies that were lower than the height of this barrier. From the perspective of classical physics, that should not happen. If the alpha particle did not possess enough energy to climb over the barrier, it should remain trapped. The classical picture looked rather like a ball sitting inside a deep valley surrounded by a hill too high for it to cross. No matter how long you waited, the ball should stay inside. Yet radioactive nuclei clearly did not behave that way. They decayed. Alpha particles escaped, and the mystery became particularly important because radioactive decay could occur over wildly different timescales. Some unstable nuclei decay almost immediately, others can persist for years, millions of years, or vastly longer. The breakthrough came in 1928. George Gamow applied the newly developed ideas of quantum mechanics to the problem of alpha decay. Independently, Ronald Wilfred Gurney and Edward Euler Condon reached closely related conclusions. Their insight was that the alpha particle did not need enough energy to climb over the nuclear barrier in the classical sense. Its quantum wave function could penetrate through it. Inside the barrier, the wave function decreases exponentially. But the barrier has a finite width. That means there can remain a small but non-zero probability amplitude beyond the region where classical motion would have been forbidden. If that happens, the alpha particle can be detected outside the nucleus. The particle has tunneled out. Nothing needed to break the energy conservation rule. The alpha particle still emerged with an energy lower than the top of the effective barrier. What changed was the assumption that it had to follow a classical trajectory over that barrier. Quantum mechanics allowed another possibility. This was a remarkable success, because it did more than provide a qualitative explanation. Tunneling could also help explain the enormous variation in radioactive half-lives. A half-life is the time required, statistically, for half the unstable nuclei in a large sample to decay. Radioactive decay is probabilistic for an individual nucleus. We cannot usually say exactly when one particular nucleus will emit an alpha particle, but for an enormous collection of identical nuclei, the overall rate is extremely predictable. The tunneling probability determines how frequently alpha particles can escape. An alpha particle trapped inside the nucleus effectively has repeated opportunities for its quantum state to penetrate the barrier. If the probability of successful transmission is relatively high, the nucleus tends to decay quickly. If the tunneling probability is extremely small, the nucleus can survive for a very long time. And because tunneling depends exponentially on the properties of the barrier, a relatively modest difference in alpha particle energy can lead to an enormous difference in decay rate. This helped explain an empirical relationship already known to physicists. In 1911, Hans Geiger and John Mitchell Nuttall had identified what became known as the Geiger-Nuttall law. They found a strong relationship between the energy of emitted alpha particles and the half-lives of the radioactive nuclei producing them. Generally, nuclei emitting higher energy alpha particles tended to decay more rapidly. Before quantum mechanics, this pattern was known from experiment but lacked a satisfying microscopic explanation. Tunneling supplied one. A higher energy alpha particle effectively faces a less severe forbidden region because its energy lies closer to the top of the potential barrier. Its wave function therefore decays less dramatically while penetrating the barrier. The probability of escape rises. Even a comparatively small change in alpha particle energy can then alter the tunneling probability by many orders of magnitude. What had looked like a strange empirical pattern suddenly followed naturally from quantum mechanics. This was one of the great early demonstrations that the new theory was doing more than producing unusual philosophical ideas. It could explain something real, something measurable, something occurring naturally inside matter. Every alpha decay is a tunneling event. The nucleus does not wait for an external machine to activate the process. No laboratory technician needs to weaken the barrier. The quantum state simply evolves according to the laws of nature, and from time to time the alpha particle appears beyond a barrier that classical mechanics says it could never cross. Radioactive material is therefore quietly performing quantum tunneling all the time. A lump of uranium sitting on a table does not look especially quantum. It does not shimmer, disappear, or behave like something from a thought experiment. Yet deep inside some of its nuclei, wave functions are extending through classically forbidden regions. Occasionally, one succeeds in reaching the other side. An alpha particle escapes. The nucleus changes, and a process that classical physics could not adequately explain becomes one of the clearest natural signatures of the quantum world. Quantum tunneling is not merely something we persuaded particles to do in a laboratory. It was already happening inside atomic nuclei long before anyone thought to ask how. The same quantum effect that allows an alpha particle to escape from an atomic nucleus also helps explain something much larger and more familiar. Why the sun shines. At the centre of the sun, matter exists as an extremely hot plasma. Temperatures reach roughly 15 million degrees, and the pressure is immense. Atomic nuclei move rapidly, colliding again and again in an environment that seems, at first glance, more than energetic enough for nuclear fusion. But there is a problem. The sun is made mostly of hydrogen, and the nucleus of ordinary hydrogen is a single proton. Protons carry positive electric charge. When two positively charged particles approach one another, the electromagnetic interaction pushes them apart. The closer the protons get, the stronger this electrostatic repulsion becomes. This creates what physicists call the Coulomb barrier. The name comes from Charles Augustin de Coulomb, whose work helped establish the quantitative law describing the electric force between charged objects. For nuclear fusion to become possible, two protons must approach extraordinarily closely. At separations comparable to the size of an atomic nucleus, the strong nuclear interaction can become important. Unlike the long-range electromagnetic repulsion, the strong nuclear interaction acts over extremely short distances and can bind protons and neutrons together inside nuclei. The difficulty is reaching that range in the first place. Classically, two protons approaching one another behave rather like two positively charged hills trying to overlap. Their kinetic energy must be large enough to overcome their electrical repulsion. And despite the enormous temperature at the Sun's centre, most protons do not have enough kinetic energy to climb over the Coulomb barrier in the classical sense. 15 million degrees is spectacularly hot to us. For the protons, however, it still leaves a substantial gap between their typical thermal energies and the energy that would be required for straightforward classical barrier crossing. If classical mechanics were the complete story, the rate of fusion in the Sun would be dramatically too small. Once again, quantum mechanics changes the question. A proton is described by a quantum state. As two protons approach one another, their wave functions encounter the effective potential barrier created by their electromagnetic repulsion. Even when their energy is below the barrier height, the wave functions do not simply terminate. They penetrate into the classically forbidden region. Most encounters still lead nowhere. The protons approach, their quantum states overlap only weakly across the barrier, and they separate again. But in a small fraction of encounters, tunneling allows the nuclei to reach sufficiently small separations that nuclear processes can occur. George Gamow developed this idea in the study of nuclear reactions involving charged particles. The probability of penetrating the Coulomb barrier is often described using what became known as the Gamow factor. The basic lesson is familiar by now. The tunneling probability depends extremely strongly on the properties of the barrier and the energy of the colliding particles. Protons moving faster have a better chance because their energy lies closer to the top of the barrier. But even particles that remain below the classical threshold can sometimes tunnel through. This creates a range of energies where two competing effects matter. Higher energy particles are rarer in the thermal population, but they tunnel more easily. Lower energy particles are much more common, but their tunneling probability is smaller. The balance between these effects produces what is often called the Gamow peak, a range of energies particularly important for nuclear reactions inside stars. Tunneling, however, is only part of the story. Getting two protons close together does not automatically mean they fuse successfully. In the Sun, the dominant energy-producing sequence is the proton-proton chain. Its first step is especially slow. Two protons approach closely enough for tunneling to overcome the Coulomb barrier, but one of those protons must then be transformed into a neutron through the weak nuclear interaction. The result is a deuterium nucleus containing one proton and one neutron, along with a positron and an electron neutrino. That weak interaction is highly improbable. In fact, it is one of the main reasons the Sun burns so slowly. If every close proton encounter immediately produced fusion, the Sun would release its nuclear fuel far more rapidly. Instead, the combination of the Coulomb barrier, quantum tunneling, and the weakness of the required nuclear transformation creates an extraordinarily gentle reaction rate. The Sun can therefore remain stable for billions of years, rather than behaving like a short-lived explosion. Once deuterium has formed, further reactions proceed more readily. The deuterium nucleus can combine with another proton to form helium-3. Later reactions between helium-3 nuclei contribute to the formation of helium-4, ultimately converting hydrogen into helium while releasing energy. Hans Albrecht Bethe played a central role in establishing the detailed theoretical understanding of how nuclear reactions power stars. In the late 1930s, Bethe analysed the reaction chains capable of sustaining stellar energy production and helped place nuclear fusion at the center of modern stellar physics. For stars like the Sun, the proton-proton chain provides the dominant source of energy. In more massive stars, other reaction pathways can become increasingly important. What matters here is that none of this works at the observed rate if the nuclei are forced to behave as classical particles. The Coulomb barrier would simply be too effective. Quantum tunneling opens a narrow possibility, not a guarantee, not a shortcut for every proton, just a small probability that some collisions reach the tiny distances required for nuclear reactions. Yet inside the Sun there are an enormous number of protons and an enormous number of collisions. A very small probability repeated across a stellar core becomes enough to sustain a star. The energy released by those fusion reactions eventually works its way outward through the Sun. After a long journey through the solar interior, part of that energy finally escapes into space as radiation. A tiny fraction reaches Earth. It warms oceans, drives weather, supports photosynthesis, and lights the room around you during the day. So quantum tunneling is not merely an obscure effect hidden in microscopic experiments. Every patch of sunlight carries the consequences of it. The Sun shines because some particles can reach places that classical physics says they should never reach, and in this case, that quiet violation of classical expectation has been illuminating the solar system for billions of years. Quantum tunneling is not only something that happens deep inside atomic nuclei or in the center of stars. It can also be used as a remarkably precise measuring tool. One of the clearest examples is the scanning tunneling microscope, an instrument capable of revealing the structure of conducting surfaces on the scale of individual atoms. The idea emerged in the early 1980s through the work of Gerd Binnig and Heinrich Rohrer at the International Business Machines Corporation Research Laboratory in Zurich. Their achievement was recognized with the Nobel Prize in Physics in 1986. The basic design sounds almost surprisingly simple. A very sharp conducting tip is brought extremely close to the surface of a conducting or semiconducting material. The tip does not need to press directly against the surface. Instead, it is held just above it, separated by an extraordinarily narrow gap. That gap may be only a fraction of a nanometer across. A nanometer is 1/1000th of a meter. At this scale, the distance between the tip and the surface can be comparable to the dimensions of individual atoms. From a classical point of view, the empty gap between them acts like an obstacle. Electrons in the tip do not have an ordinary conducting path into the sample. There is no wire bridging the space. There is no tiny mechanical connection. The narrow region between tip and surface behaves as an effective potential energy barrier. Classically, electrons with insufficient energy to cross that barrier should remain confined to one side. Quantum mechanics provides another possibility. The electron wave functions associated with the tip can extend into the gap. The electronic states of the surface extend into it as well. If the separation is sufficiently small and an appropriate voltage difference is applied, electrons can tunnel through the barrier between tip and sample. The result is a measurable electric current known as the tunneling current. This current can be extremely small, often on the scale of billionths of an ampere. But its most useful property is not merely that it exists, it is how sensitive it is to distance. Because tunneling probability depends exponentially on barrier width, even a very small change in the gap between the tip and the surface can produce a dramatic change in the current. Move the tip slightly closer and the tunneling current can increase sharply. Move it slightly farther away and the current can collapse. A change in separation of only a fraction of a nanometer can therefore become clearly measurable. Something that seemed like a limitation of tunneling suddenly becomes a tremendous advantage. the wave function decays so rapidly across the gap that the tunneling current acts as an exquisitely sensitive probe of distance. To examine a surface, the tip is slowly scanned across it. Electronic control systems can monitor the tunneling current continuously. One common method adjusts the height of the tip so that the current remains approximately constant. If the surface rises beneath the tip is moved upward. If the surface falls away, the tip moves downward. By recording those tiny vertical adjustments while the tip travels across the sample, researchers can construct a detailed map of the surface. The result can reveal features associated with individual atoms. It is tempting to describe these images simply as photographs of atoms, but that would be slightly misleading. A scanning tunneling microscope does not work like an ordinary camera. It does not collect visible light bouncing from tiny atomic spheres. The measured signal depends on the tunneling current, which in turn depends on both the tip surface separation and the local electronic structure of the material. So the images reveal information about the arrangement of atoms and the local density of available electronic states. That distinction is important. Atoms do not have hard outer surfaces like microscopic billiard balls. Their electronic structure is quantum mechanical. The scanning tunneling microscope is therefore not merely looking at geometry. It is probing the quantum states that exist near the surface. This makes the instrument useful for far more than producing striking atomic scale images. Researchers can study surface defects, individual adsorbed atoms and molecules, electronic states, semiconductor structures, and the arrangement of atoms in carefully prepared materials. Under suitable conditions, the tip can even be used to manipulate individual atoms. One of the most famous demonstrations came in 1989, when researchers at the International Business Machines Corporation moved individual xenon atoms across a nickel surface and arranged them into letters. The experiment was memorable because it showed just how directly scientists could begin interacting with matter at the atomic scale. But beneath the visual spectacle was the same quiet quantum mechanism. Electrons were crossing a barrier they could not classically cross. The scanning tunneling microscope also illustrates something important about scale. Across a wide gap, the tunneling current would become effectively undetectable. Across an extremely narrow one, it becomes measurable. This is exactly what the exponential decay of the wave function predicts. The instrument therefore converts one of the strangest features of quantum mechanics into a practical ruler. A tiny change in distance becomes a large change in current. And because the sensitivity is so extreme, researchers can distinguish variations comparable with the dimensions of individual atoms. There is something wonderfully circular about that. Quantum tunneling once seemed to suggest that particles were behaving in an almost impossible way, yet the effect became so predictable that engineers learned to build instruments around it. The apparently forbidden crossing became a source of precision. A single electron does not need a physical bridge between the tip and the surface. Its quantum state can extend across the narrow barrier, creating a finite transmission probability. Repeat that process with enormous numbers of electrons, and the result is a steady measurable current. Monitor that current carefully enough, and the invisible behavior of wave functions becomes a tool for exploring the atomic world. What looked like a loophole in classical intuition becomes an instrument of extraordinary reliability. As technology has become smaller, quantum tunneling has moved from being a strange feature of microscopic physics to something engineers have to think about constantly. The reason is simple. When barriers become thin enough, electrons no longer behave as though those barriers are completely solid. At large scales, an insulating layer may seem perfectly effective. It separates one conducting region from another and prevents charge from flowing between them. but shrink that insulating layer down towards the nanometer scale, and quantum mechanics begins to interfere with the tidy classical picture. Electron wave functions can extend into the barrier. If the barrier is thin enough, some amplitude can survive to the other side, and that makes tunneling technologically important. One of the earliest devices designed specifically to exploit this effect was the tunnel diode. The Japanese physicist Ryo Esaki developed the device in the late 1950s while working with heavily doped semiconductor materials. In an ordinary semiconductor junction, electrons are often described in terms of energy bands, ranges of allowed quantum states within the solid. By carefully altering the concentration of impurities in the semiconductor, engineers can change how those electronic states are populated. In a tunnel diode, the two sides of the junction are doped so heavily that the region separating them becomes extremely thin enough for tunneling to matter. When a suitable voltage is applied, occupied electronic states on one side can line up with available states on the other. Electrons can then tunnel directly across the junction. As the applied voltage changes, however, that alignment changes too. At first, increasing the voltage allows more electrons to tunnel, so the current rises. Then something unusual happens. Further increasing the voltage causes the alignment between occupied and available states to become worse. The tunneling current falls. This produces a region known as negative differential resistance. Normally, increasing the voltage across a device tends to increase the current through it. In this particular region of a tunnel diode, the opposite occurs. The voltage rises while the current decreases. That unusual behavior made tunnel diodes useful in certain high-speed electronic circuits, and provided a particularly direct demonstration of controlled quantum tunneling in a solid. Another tunneling process appears when very strong electric fields reshape the barrier experienced by electrons. This is associated with the work of Clarence Melvin Zener. In semiconductors exposed to sufficiently strong fields, electrons can tunnel directly between energy bands. This is often called Zener tunneling, or band-to-band tunneling. It is important to distinguish this from avalanche breakdown. Both processes can occur when large electric fields are present, but they are not the same mechanism. In avalanche breakdown, charge carriers gain enough energy from the field to collide with atoms in the material and create additional mobile charge carriers. Those new carriers accelerate and produce further collisions, leading to a multiplying cascade. Zener tunneling instead arises directly from quantum transmission between electronic states across a narrow energy barrier. The balance between these mechanisms depends on properties such as the material, the electric field, and the structure of the semiconductor junction. Strong electric fields can also produce another important tunneling phenomenon known as Fowler-Nordheim tunneling. Ralph Howard Fowler and Luther Wolfgang Nordheim developed the theoretical description in the late 1920s. Here, an electric field modifies the potential barrier that normally confines electrons inside a material. The barrier effectively becomes narrower and more sharply sloped. Electrons can then tunnel through it and escape from the surface. This phenomenon plays an important role in field emission, where electrons are extracted from a solid by extremely strong electric fields. Once again, the underlying lesson is that changing the shape of a barrier can change tunneling probability dramatically. Modern electronics encounters the same principle constantly. Many electronic devices contain extremely thin insulating layers. Ideally, those layers keep electrons confined to the regions where engineers want them. But as device dimensions shrink, the insulating barriers can become thin enough that electrons begin tunneling through them. Sometimes this is useful. Sometimes it is exactly what engineers do not want. In very small transistor structures, unwanted tunneling can create leakage current. Even when a transistor is supposed to be switched off, electrons may still have a small probability of crossing a thin barrier. Multiply that tiny leakage across billions of devices, and it can contribute to wasted power and unwanted heating. This is one reason continued miniaturization becomes increasingly difficult. The smaller the structures become, the harder it is to pretend that electrons behave like classical particles confined neatly by tiny walls. Quantum mechanics begins to set practical engineering limits, but tunneling can also be deliberately harnessed. Certain forms of non-volatile memory use carefully controlled electron tunneling to move charge into or out of electrically isolated regions. Non-volatile means that the stored information can remain even when electrical power is removed. In some memory technologies, electrons are forced through a thin insulating barrier during writing or erasing. Once trapped in a suitable region, the stored charge changes the electrical behavior of the device and can represent information. The exact mechanisms vary between different memory designs, so tunneling should not be treated as a universal explanation for every modern storage technology. But in several important architectures, quantum transmission through insulating barriers is central to how information is written, retained, or removed. This creates an interesting reversal. At first, quantum tunneling seems like an exotic exception to common sense. A particle appears where a classical barrier says it should not be able to go. Yet once electronic structures become sufficiently small, that supposedly exotic effect becomes routine. Engineers must calculate it. They must control it. Sometimes they exploit it. Sometimes they spend enormous effort trying to prevent it. A barrier only a few nanometers thick can no longer be treated as an unquestionable wall. For an electron, it may be more like a probability filter. Make it thicker and transmission collapses. Make it thinner and tunneling can rise dramatically. Change the electric field and the shape of the barrier changes with it. Modern electronics therefore sits in a strange but practical middle ground. The devices in our hands look entirely ordinary. Inside them, however, electrons are constantly obeying rules that classical physics would never have permitted. At sufficiently small scales, quantum tunneling stops being a curiosity. It becomes part of engineering. Quantum tunneling becomes even stranger when it is no longer useful to imagine one isolated electron crossing a barrier at a time. Under the right conditions, an entire coherent quantum state can take part. This happens in superconductors. A superconductor is a material that, when cooled below a characteristic critical temperature, can conduct electrical current with zero direct current electrical resistance. It also exhibits distinctive magnetic behavior, including the expulsion of magnetic fields from its interior under appropriate conditions. The microscopic explanation of conventional superconductivity depends on a remarkable collective state formed by electrons. Ordinarily, electrons repel one another because they carry the same negative electric charge. Inside certain materials at sufficiently low temperatures, however, interactions between electrons and vibrations of the crystal lattice can produce an effective attraction. Leon Neil Cooper showed that even a weak attractive interaction near the appropriate electronic energy can cause electrons to form correlated pairs. These became known as Cooper pairs. The paired electrons do not simply become little two-electron molecules wandering independently through the solid. Instead, enormous numbers of Cooper pairs can participate in a coherent quantum state described by a common macroscopic wave function. This coherence is crucial. Normally, quantum effects involving phase relationships are easiest to notice in tiny, carefully isolated systems. In a superconductor, quantum coherence can extend across distances enormous, compared with the scale of individual atoms, and that creates an extraordinary form of tunneling. Imagine placing two superconductors extremely close together while separating them with a very thin insulating layer. Classically, the insulator should interrupt the conducting path. Electrons cannot simply flow through an ideal insulator as they would through a metal. But if the insulating barrier is sufficiently thin, the superconducting quantum states on either side do not remain completely independent. Their wave functions can extend into the barrier. In 1962, Brian David Josephson, then a young researcher at the University of Cambridge, predicted that Cooper pairs could tunnel coherently between two superconductors separated by such a barrier. The structure became known as a Josephson junction. One of Josephson's predictions was especially remarkable. Under suitable conditions, a supercurrent can flow through the insulating barrier even when there is no ordinary voltage difference across the junction. This is the direct current Josephson effect. The current does not arise because the insulating layer has somehow stopped being an insulator, nor does it require individual electrons to acquire enough energy to climb over the barrier. Instead, the coherent superconducting states on the two sides possess quantum phases, and the difference between those phases determines the supercurrent that can tunnel across the junction. The phase of a quantum state is difficult to picture directly, but it plays a role somewhat like the relative timing of waves. Two waves can reinforce or cancel one another depending on how their oscillations line up. In a Josephson junction, the relative phase of the superconducting wave functions has observable physical consequences. A current can depend directly upon it. That already makes the junction strikingly different from an ordinary electrical connection. Then there is the alternating current Josephson effect. If a constant voltage is applied across the junction, the phase difference between the superconductors changes continuously with time. As a result, the tunneling supercurrent oscillates. Most importantly, the oscillation frequency is tied extraordinarily precisely to the applied voltage through fundamental constants of nature. The relationship can be written in words as the frequency equals 2 times the elementary electric charge multiplied by the voltage divided by Planck's constant. This exceptionally precise connection between frequency and voltage has made the Josephson effect enormously valuable in metrology, the science of precise measurement. Josephson junctions are used in systems that realize highly accurate voltage standards. Rather than relying only on the properties of some manufactured component, the relationship is anchored in fundamental quantum physics. The same junctions can also be arranged to measure extraordinarily weak magnetic fields. One important instrument is called the superconducting quantum interference device. It typically contains superconducting paths interrupted by Josephson junctions. Because the superconducting state remains coherent around the structure, different quantum amplitudes can interfere. The magnetic field passing through the device changes the phase relationships, which in turn alters the measurable current or voltage. The sensitivity can be extraordinary. Superconducting quantum interference devices are used in fields ranging from condensed matter research to geophysics and biomagnetism, where extremely weak magnetic signals may be important. Josephson junctions have also become central components of many superconducting quantum circuits. In these devices, engineers deliberately use Josephson tunneling and the nonlinear electrical properties of the junction to create controllable quantum systems. Such circuits form the basis of several types of superconducting quantum bits used in quantum computing research. What makes all of this especially revealing is that tunneling is no longer behaving like a series of completely unrelated particles occasionally getting lucky. Cooper pairs tunnel coherently. the phase relationship of the collective quantum state survives strongly enough to affect measurable electrical currents. Interference appears. Precise frequencies emerge. Macroscopic instruments can be built around the effect. This exposes something deeper about quantum tunneling. Tunneling is fundamentally about the behavior of quantum states across barriers. Sometimes the state belongs primarily to one microscopic particle. In a superconductor, the relevant quantum description can involve an enormous number of correlated particles acting coherently. The barrier remains real. The insulating layer still separates two pieces of material. Yet the quantum states do not respect that boundary in the absolute way classical intuition expects. Their wavefunctions penetrate it. Their phases remain connected through the tunneling interaction, and a measurable current can cross a region that ordinary classical conduction says should interrupt the circuit. What began as the strange possibility of one particle appearing beyond a forbidden barrier therefore becomes something much grander. Quantum tunneling can carry coherence with it. And when that coherence belongs to a collective state containing immense numbers of paired electrons, one of the smallest effects in physics becomes visible in the behavior of an entire electrical device. A single quantum barrier is already enough to produce behavior that classical physics would never predict. But place two barriers close together, and the situation becomes even more interesting. Imagine an electron approaching one thin barrier, followed by a small region of lower potential energy, and then a second barrier. The space between those two barriers forms what physicists call a quantum well. Classically, this looks worse than the original problem. If the electron does not possess enough energy to cross the first barrier, adding a second barrier behind it hardly seems helpful. Two obstacles should be more difficult than one. Quantum mechanics does not always agree. The wave function of the electron can penetrate the first barrier and extend into the quantum well between them. Once there, it can be partially reflected by both barriers. The result is a collection of probability amplitudes travelling back and forth through the central region. And because these amplitudes behave like waves, they can interfere. At some energies, the interference is mostly destructive. Different contributions arrive out of phase and partially cancel one another. The probability of the electron crossing the entire structure remains very small. At certain special energies, however, something quite different occurs. The wave function fits the central region in just the right way for the returning amplitudes to reinforce one another. This is resonant tunneling. The energy of the incoming electron becomes aligned with a quantum state that can exist temporarily within the well between the barriers. These states are often described as quasi-bound states. They resemble bound states because the electron can have an enhanced probability of occupying the region between the barriers for a time. But they are not perfectly confined. The surrounding barriers are finite, so the state can still leak away through tunneling. When the incoming electron energy matches one of these resonant states, constructive interference can dramatically increase the probability of transmission through the entire structure. In an idealized symmetric system, the transmission probability at resonance can even approach 1. That means a pair of barriers that appears highly resistant at most energies can become almost completely transparent at particular ones. This is a striking reminder that quantum tunneling is not simply a matter of asking how high or how wide a barrier is. Phase matters too. Interference matters. The entire arrangement of the quantum state matters. There is a loose analogy with standing waves, although it should not be taken too literally. A vibrating string fixed at both ends supports certain preferred patterns because only particular wavelengths fit neatly between the boundaries. Likewise, the quantum well between two barriers supports particular energy conditions under which the probability amplitudes reinforce one another especially effectively. But the electron is not a tiny string vibrating between two walls. The relevant quantities are quantum probability amplitudes, and the observable result is a change in the likelihood of transmission. Move slightly away from the resonant energy, and the situation can change sharply. The amplitudes no longer line up in the same favourable way. Constructive interference weakens. Transmission falls. So the very same barrier structure can behave almost like an opaque wall for one electron energy and a surprisingly open doorway for another. Engineers have learned to exploit this sensitivity. A resonant tunneling diode is a semiconductor device built from extremely thin layers of different materials. These layers are arranged so that two potential barriers surround a narrow quantum well. Electrons approaching the structure encounter the same basic physics. At certain applied voltages, the energies of incoming electrons align with an allowed resonance state inside the well. Tunneling becomes much more probable and the electrical current rises. Change the voltage further, however, and the alignment becomes worse. The resonant condition is lost. Fewer electrons can tunnel through efficiently, and the current can decrease even while the applied voltage continues to increase. This produces a region of negative differential resistance, similar in broad electrical behavior to the tunnel diode, but arising from a carefully engineered double barrier resonance. Such devices have been investigated for high-frequency electronics, oscillators, switching applications, and other specialized uses where extremely rapid quantum transport can be valuable. Their operation depends on structures whose dimensions may be only a few nanometers. At that scale, the wave nature of electrons is not a small correction to classical engineering. It is the central design principle. Resonant tunneling also reveals something important about the idea of a barrier itself. In classical physics, an obstacle has a fairly straightforward meaning. If you do not possess enough energy to cross it, you stop. Adding another obstacle cannot somehow make the first one easier. Quantum mechanics works differently, because an electron approaching several barriers is described by one coherent quantum state. The amplitudes associated with different reflections and transmissions combine. They carry relative phases. Those phases determine whether the possibilities reinforce or suppress one another. So the probability of reaching the far side does not depend only on the properties of each barrier considered separately. It can depend on the relationship between all of them. This is one reason the picture of an electron as a tiny ball trying to force its way through a wall eventually becomes misleading. A classical ball cares about whether it has enough energy to clear the obstacle. A quantum particle also cares in a very real mathematical sense about how its wave function fits the entire landscape. Sometimes the barriers suppress transmission almost completely. Sometimes they cooperate through interference to produce a resonance. And under those special conditions, two barriers can allow far more transmission than simple classical reasoning would ever suggest. The particle has not become more energetic. The walls have not vanished. The quantum amplitudes have simply found a way to reinforce one another. And once that happens, a structure designed from barriers can become unexpectedly transparent. At some point, almost every discussion of quantum tunneling arrives at the same irresistible question. If particles can pass through barriers they should not be able to cross, could you do the same thing? Could a person, at least in principle, walk straight through an ordinary wall? Quantum mechanics does not suddenly switch off when objects become large. The atoms in your body are quantum systems. The atoms in the wall are quantum systems. Electrons, protons, and nuclei continue to obey quantum laws whether they are sitting alone in a laboratory or assembled into something much larger. But that does not make walking through a wall remotely plausible. The first problem is mass. Tunneling probability depends very strongly on the mass of the object involved. For a simple barrier, the probability falls approximately exponentially, with a combination of quantities including the barrier width, the mass of the particle, and the difference between the particle's energy and the height of the barrier. That exponential dependence is ruthless. An electron is extraordinarily light. Its mass is roughly 9 times 10 to the minus 31 kilograms. For such a particle, tunneling through a barrier only a fraction of a nanometer wide can be significant enough to measure routinely. A human being, by comparison, might have a mass of several tens of kilograms. That is not merely a little heavier. It is heavier by an almost incomprehensible factor. If we attempted to insert an entire person into the same type of tunneling calculation, the probability would be suppressed so dramatically that the result would be effectively indistinguishable from zero. And the barrier is worse too. In nanoscale devices, tunneling may occur across distances measured in fractions of a billionth of a meter. An ordinary wall might be centimeters thick. A centimeter is tens of millions of times wider than a typical atomic scale tunneling distance. Because the suppression depends exponentially on width, making a barrier millions of times thicker is not like making a hill millions of times harder to climb. It destroys the tunneling probability at a rate that quickly leaves ordinary language behind. There is another complication. A human being is not one quantum particle. A body contains somewhere around 10 to the 28 atoms, depending on exactly how the estimate is made. Each atom contains electrons and a nucleus, and each nucleus contains protons and neutrons. For your entire body to tunnel through a wall while remaining recognizably you, it would not be enough for one electron somewhere in your little finger to tunnel a short distance. Individual particles inside matter already undergo quantum effects. Electrons can tunnel in chemical and electronic systems. Protons can tunnel under suitable conditions. None of this makes the entire object containing those particles appear on the opposite side of a wall. For whole body tunneling, the coordinated quantum state of an enormous number of constituent particles would have to evolve in an extraordinarily specific way. The positions and relationships between those particles would have to remain organized well enough for the body to emerge intact. The challenge is not simply that one particle must tunnel through one barrier. It is that a staggeringly complex macroscopic system would have to behave coherently as a single tunneling object across an enormous distance by quantum standards. That leads to another reason the everyday world looks classical. Environmental decoherence. A quantum system rarely exists in perfect isolation. It interacts continuously with its surroundings. Photons strike it. Air molecules collide with it. Atoms vibrate thermally. Electromagnetic fields fluctuate around it. Internal degrees of freedom interact with one another. Each of these interactions can carry away information about the quantum state. Decoherence describes the process by which delicate phase relationships between different parts of a quantum superposition become effectively dispersed into the surrounding environment. Wojciech Hubert Zurich has played a major role in developing the modern theory of decoherence, and in explaining how apparently classical behavior can emerge from underlying quantum mechanics. The key point is not that the wave function mysteriously stops existing for large objects. Rather, large objects interact with enormous numbers of environmental degrees of freedom so quickly and so strongly that coherent superpositions of macroscopically distinct states become extraordinarily difficult to maintain. A small quantum system can sometimes be isolated carefully enough for interference to survive. A person standing in a room cannot. Your body is constantly interacting with light, air, heat, the floor, internal molecular motion, and countless other pieces of the environment. Any hypothetical coherent state involving you being on one side of a wall and also having amplitude on the other would become entangled with that environment almost immediately. The quantum phases required for observable whole-body interference would be effectively lost into an astronomical number of surrounding degrees of freedom. This is one reason macroscopic objects appear to occupy definite locations even though they are ultimately made from quantum ingredients. There is an important subtlety here. Decoherence is not usually the main mathematical reason that a person fails to tunnel through an ordinary wall. Even before worrying about environmental interactions, the tunneling probability associated with the enormous mass and width involved is already fantastically suppressed. Decoherence then adds another profound obstacle to maintaining the kind of coherent macroscopic quantum behavior required for the scenario. So quantum mechanics does not provide a tiny but practical chance that you might occasionally lean against a wall and suddenly find yourself in the next room. For all realistic purposes, that probability is zero. Waiting longer does not make the idea meaningfully better. Even time spans vastly exceeding the age of the universe would not turn such an absurdly suppressed event into something worth worrying about. The comparison with electron tunneling can therefore be misleading unless scale is kept firmly in mind. An electron crossing a barrier a fraction of a nanometer wide is a quantum process involving an extremely light particle and an extremely narrow forbidden region. A human crossing a centimeter-thick wall is an entirely different physical proposition. The distance is vastly larger. The effective mass is vastly larger. The internal complexity is enormous, and interaction with the environment is relentless. Quantum mechanics allows some things that classical intuition forbids. It does not make every imaginable event reasonably likely. That distinction is important. A quantum probability can be non-zero in principle and still be so unimaginably small that nature will never provide a realistic opportunity to observe it. So you can safely use doors. The electrons inside the wall may tunnel across microscopic barriers from time to time. The person standing in front of it will not. One of the most tempting questions in quantum tunneling is also one of the hardest to answer cleanly. How long does the crossing actually take? With an ordinary object, this would seem straightforward. If a car enters a tunnel at one moment and emerges at another, we can subtract the two times and find the duration of the journey. If a stone passes through a doorway, we can track its position continuously and calculate how long it spent between the two sides. Quantum tunneling is more subtle because the particle does not come with one universally agreed classical path through the barrier. That makes the idea of a single transit time surprisingly difficult to define. Physicists refer to this as the tunneling time problem. The difficulty is not that quantum mechanics gives no predictions. It gives extremely precise predictions for reflection probabilities, transmission probabilities, energy dependence, and many other measurable quantities. The problem is deciding exactly what quantity should count as the time spent tunneling. One possibility is to ask how long the center of a transmitted wave packet appears to be delayed compared with some reference motion. Another is to ask how long the quantum state significantly occupies the barrier region. Another is to introduce some physical clock that interacts weakly with the particle while it is inside the barrier. These are not necessarily the same thing, and because they correspond to different experimental procedures, they can produce different characteristic times without any contradiction. This is a useful reminder that time in quantum mechanics is not always attached to a tiny hidden stopwatch carried by the particle. The definition has to be connected to something that can actually be measured. One famous complication was identified by Thomas Hartmann in the 1960s. What became known as the Hartmann effect appears in certain theoretical descriptions of tunneling through sufficiently opaque barriers. One might expect that making a barrier thicker would always make the tunneling delay proportionally longer. After all, if something travels through twice as much material, ordinary intuition says it should take roughly twice as long. But for some definitions of tunneling delay, the calculated delay can begin to level off as the barrier becomes thicker. It does not continue increasing in the simple classical way. Taken carelessly, this can create a very strange impression. If the effective delay stops growing while the barrier keeps getting wider, one might divide distance by time and obtain an apparent speed greater than the speed of light. That sounds dramatic. It does not mean that a particle has become a faster than light messenger. The transmitted wave packet is reshaped by the tunneling process. Different components of the incoming packet are transmitted with different efficiencies and phases. As a result, the location of the peak of the outgoing packet can shift in ways that do not correspond to one little object racing through the barrier at that apparent velocity. This distinction between group delay and signal transmission is crucial. Relativity forbids usable information from being transmitted faster than light. Tunneling experiments do not provide a loophole around that restriction. The early appearance of a reshaped transmitted peak cannot be used to send a genuinely new causal signal into the future faster than light would allow. So an apparent superluminal tunneling velocity is not evidence that relativity has quietly failed inside thin barriers. It is evidence that defining velocity from the motion of a wave packet peak can become misleading in a strongly filtering quantum process. Another approach to tunneling time uses what is called a Larmor clock. The idea relies on the behavior of a particle possessing a quantum property such as spin in a weak magnetic field. A magnetic field placed only within the barrier region can cause the spin to precess. The amount of precession can then contain information about how strongly, or for how long, in an operational sense, the quantum state interacted with that region. Martin Bittaker developed influential treatments of this approach and other tunneling time concepts. The Larmor clock does not reveal a tiny classical trajectory hidden behind the wave function. Instead, it turns the question into something experimentally meaningful. How much does a weak interaction confined to the barrier alter a measurable property of the transmitted particle? That is a very different question from simply imagining a stopwatch starting as the particle crosses the front edge and stopping when it crosses the back. Modern experiments have pushed these questions into extraordinarily short timescales. Attosecond physics deals with intervals on the order of 1/quintillionth of a second. At these scales, researchers can investigate how electrons respond to intense laser fields and how tunneling-related ionization processes unfold. In strong field ionization, an intense electromagnetic field can distort the potential binding an electron to an atom. The barrier becomes narrow enough that the electron can tunnel out. Researchers then use precisely controlled laser pulses and related techniques to infer timing information about the release process. These experiments are remarkable, but they are not identical to the simple textbook problem of a particle approaching a static rectangular barrier. The potential itself is changing with time. The electron begins in a bound atomic state. The surrounding electromagnetic field can be extremely strong, so conclusions drawn from strong field attosecond experiments have to be connected carefully to the broader tunneling time debate. Even defining when tunneling begins can be subtle. Does it begin when the wave packet first reaches the front of the barrier? When appreciable probability amplitude enters the forbidden region? When the particle leaves a bound state? And what counts as arrival on the other side? The first appearance of amplitude? The peak of a wave packet? The average detection time? Different choices can answer slightly different physical questions. That is why there is no single tunneling time that every method is required to produce. This uncertainty should not be confused with uncertainty about whether tunneling happens. The existence of tunneling is extremely well established. Particles are transmitted through barriers. Measured currents depend on tunneling probabilities. Radioactive nuclei decay through tunneling. Semiconductor devices and scanning tunneling microscopes rely upon it. Those facts are not in doubt. What remains subtle is how to translate a process described by an evolving quantum state into the familiar classical sentence, "The particle spent exactly this long inside the barrier." Quantum mechanics may simply not contain one unique quantity corresponding to that sentence in every possible experiment. So the question of how long tunneling takes does not have one beautifully simple answer. There are several useful definitions, each tied to a particular measurement or theoretical purpose. And that may be the more interesting lesson. The difficulty is not merely that the event happens too quickly to measure. It is that the familiar idea of travel time quietly assumes a definite path. Quantum tunneling is precisely one of the places where that assumption becomes difficult to maintain. Quantum tunneling does not only appear in nuclear physics, electronics, or carefully engineered laboratory devices. It can also influence chemistry. A chemical reaction is often described as a transformation from one arrangement of atoms into another. Bonds break, new bonds form, electrons shift, nuclei move, and the system settles into a different molecular configuration. But those transformations do not always happen freely. Between the starting arrangement and the final one, there can be an energy barrier. Classically, the reacting molecules need enough thermal energy to climb over that barrier. This is the familiar idea of activation energy. Heat the system, and a larger fraction of molecules can reach the required energy. Cool it down, and the reaction usually slows. Quantum mechanics adds another possibility. If the particle that needs to move is sufficiently light, and if the barrier is sufficiently narrow, its wave function can penetrate through the barrier rather than requiring enough energy to pass over it. Hydrogen is particularly important here. The nucleus of ordinary hydrogen is a single proton. A proton is much heavier than an electron, but it is still light enough for tunneling to become significant in certain molecular environments. In proton transfer reactions, a proton may need to move from one part of a molecule to another or between neighboring molecules. Classically, it should have to climb over the potential energy barrier separating those configurations. Quantum mechanically, there can be a finite probability that it tunnels through. This effect becomes especially noticeable at low temperatures. When a system is warm, ordinary thermal motion can supply enough energy for many particles to cross reaction barriers classically. As the temperature falls, that thermal route becomes increasingly suppressed. Tunneling, however, does not disappear simply because the particle lacks enough thermal energy to reach the top. The probability may still be small, but it can remain significant enough to sustain a reaction that classical thermal activation would predict should become extraordinarily slow. Electrons provide another important example. In many chemical and biological systems, an electron needs to move from one molecular site to another. The electron does not necessarily travel between the two sites as though it were a tiny bead following a classical path through the intervening material. Its quantum state can extend across the molecular environment, and under suitable conditions, electron transfer can involve tunneling between electronic states. The probability depends on factors such as separation, electronic coupling, the surrounding molecular structure, and the energetic relationship between the initial and final states. Rudolf Marcus developed the theoretical framework now known as Marcus theory for understanding electron transfer reactions. His work showed how the energy landscape of the reacting molecules and their environment determines the likelihood and rate of electron transfer. One important idea is that the surrounding molecules must often reorganize as charge moves from one place to another. The reaction depends not only on the electron itself, but also on whether the molecular environment reaches a configuration in which transfer becomes favorable. Quantum tunneling can contribute to the actual transition between the relevant electronic states. Marcus theory therefore provides a broader energetic framework for electron transfer, while tunneling describes one of the quantum mechanisms by which the electronic transition can occur. Chemists have also found useful ways to identify tunneling experimentally. One of them involves isotopes. Ordinary hydrogen contains one proton in its nucleus. Deuterium, a heavier isotope of hydrogen, contains one proton and one neutron. Chemically, hydrogen and deuterium are very similar because they possess the same electric charge and the same number of electrons when neutral, but their nuclear masses are substantially different, and tunneling is extremely sensitive to mass. Replacing hydrogen with deuterium can therefore reduce the probability of tunneling through the same molecular barrier. If a reaction involving hydrogen proceeds noticeably faster than the corresponding reaction involving deuterium, the difference is known as a kinetic isotope effect. Not every kinetic isotope effect proves tunneling by itself, because differences in vibrational energies and other molecular properties also matter. But unusually strong temperature-dependent isotope effects can provide evidence that hydrogen tunneling is contributing to the reaction mechanism. This has become particularly interesting in biochemistry. Enzymes accelerate chemical reactions inside living systems. In some enzyme-catalyzed reactions involving hydrogen transfer, experiments suggest that proton or hydrogen atom tunneling can contribute to the observed reaction rate. That does not mean enzymes are mysterious quantum machines whose entire function depends on exotic tunneling. Their effectiveness comes largely from conventional chemical mechanisms, including precise molecular geometry, electrostatic interactions, binding effects, and changes to reaction energy landscapes. But in certain cases, once an enzyme has arranged the reacting molecules appropriately, tunneling can assist the movement of a light hydrogen nucleus across a remaining barrier. The same physics can become important in environments far removed from biology. Interstellar space contains regions so cold that many ordinary thermally activated chemical reactions would proceed extremely slowly. Inside dense molecular clouds, temperatures can fall to only a few tens of degrees above absolute zero, and dust grains become coated with thin layers of frozen molecules. Atoms and molecules landing on these cold surfaces can react to form new compounds. Hydrogen atoms are especially mobile and especially light. Quantum tunneling can help them cross energy barriers on or within icy grain surfaces, even when the surrounding material is extremely cold. This contributes to the chemistry that produces molecules in interstellar clouds before stars and planets have even formed. The details of astrochemical reaction networks are complicated, and tunneling is not important for every reaction. But for light particles encountering narrow barriers, it can allow chemistry to continue in conditions where classical thermal motion alone would struggle. This brings the idea of tunneling into a very different setting. The barrier does not need to be a piece of semiconductor or the edge of an atomic nucleus. It can be the energy landscape separating two molecular arrangements. The tunneling object does not need to be an alpha particle. It can be an electron, a proton, or a hydrogen atom. The same underlying principle remains. A sufficiently light quantum particle can possess a wave function that reaches into a region that classical mechanics would forbid. If enough amplitude survives across that barrier, a chemical transformation can occur without the particle ever having enough energy to climb over it in the ordinary classical sense. Quantum tunneling is therefore not an isolated trick performed under exotic conditions. It is woven quietly into chemistry itself, influencing reactions in laboratories, living molecules, cold interstellar clouds, and countless microscopic systems where barriers are narrow enough for quantum probability to matter. Quantum tunneling begins with a very simple picture. A particle approaches a barrier. Classical physics says it does not have enough energy to cross. Quantum mechanics says the wave function can still extend into that forbidden region and, if the barrier is finite, sometimes beyond it. From that one idea, an enormous range of physical effects follows. An alpha particle can escape from an atomic nucleus. Protons can penetrate the Coulomb barrier inside stars. Electrons can cross nanometer-scale gaps in microscopes and semiconductor devices. Cooper pairs can tunnel coherently across Josephson junctions. Hydrogen nuclei can tunnel during certain chemical reactions. These are not separate tricks requiring different versions of quantum mechanics. They are different expressions of the same underlying principle. The simple rectangular barrier often used to introduce tunneling is therefore useful but deliberately artificial. Real physical systems rarely contain perfectly sharp walls with completely flat regions on either side. A molecular reaction may involve a complicated landscape of nuclear positions. An atomic nucleus contains interactions varying continuously with separation. A semiconductor junction may have electric fields that bend the potential gradually across a material. In more realistic quantum mechanics, the state can evolve through a multidimensional potential energy landscape containing valleys, ridges, wells, saddles, and barriers. The mathematics becomes more difficult. The core idea does not change. Classically, a system may be trapped in one region because every ordinary trajectory towards another configuration requires more energy than the system possesses. Quantum mechanically, there can still be a non-zero transition amplitude connecting the two. Even the word particle eventually becomes too narrow. Modern fundamental physics describes nature using quantum fields. An electron is understood as an excitation of an electron field. Photons are excitations of the electromagnetic field. Quarks and other particles are described through their respective quantum fields. Within quantum field theory, tunneling can refer not merely to one particle crossing a spatial barrier, but to an entire field changing from one configuration to another. The barrier now exists in configuration space rather than necessarily corresponding to a literal obstacle at some position in a room. This sounds dramatically more abstract, but the connection with ordinary tunneling remains recognizable. There can be one configuration that is classically stable or temporarily trapped. Another configuration may exist elsewhere in the relevant energy landscape. Classical evolution cannot carry the system between them at the available energy. Quantum theory can still assign a non-zero amplitude to the transition. One mathematical tool used to study certain tunneling processes in quantum theories is the instanton. An instanton is a special solution that appears when quantum problems are reformulated using a mathematical treatment involving imaginary time. It should not be imagined as a tiny object physically darting through a barrier. Instead, it provides a way of calculating non-perturbative quantum effects, meaning phenomena that cannot always be captured by simply treating an interaction as a small correction and expanding the answer term by term. Instantons became especially important in the study of gauge theories. Alexander Markovich Polyakov and Gerardus Hooft made major contributions to understanding these structures and their role in quantum field theory during the 1970s. Their work helped reveal that quantum fields can possess physically significant behavior, connecting configurations that classical reasoning would treat as distinct. This is tunneling expressed in a much more sophisticated language. An even more dramatic example appears in the idea of false vacuum decay. In quantum field theory, a vacuum does not simply mean empty space. It refers to a lowest or locally stable state of one or more quantum fields. A false vacuum is a hypothetical field configuration that is locally stable, but not necessarily the lowest energy state available. An analogy would be a ball resting in a shallow valley when a deeper valley exists elsewhere. Classically, if the ridge between them is too high, the ball remains trapped. Quantum mechanically, the field may possess a non-zero probability of tunneling into the lower energy configuration. Sidney Richard Coleman developed an influential semi-classical treatment of this process. In such a description, a region of the lower energy state can nucleate through quantum tunneling and, under suitable theoretical conditions, expand. This idea appears in discussions of early universe cosmology and quantum field theory. It should be treated carefully. False vacuum decay is not simply an enormous version of an electron passing through a thin insulating layer, and there is no established observation showing that our present vacuum is about to undergo such a transition. It is a theoretical example demonstrating how far the mathematical concept of tunneling can be extended. The important connection is not the appearance of a literal wall. It is the existence of classically separated configurations and a non-zero quantum amplitude connecting them. That same pattern has been present all along. The alpha particle does not need to borrow energy to climb out of the nucleus. The proton inside the Sun does not suddenly become hot enough to fly classically over the Coulomb barrier. The electron in a tunneling microscope does not discover a microscopic bridge across the vacuum gap. And a quantum field undergoing a tunneling transition does not receive some mysterious external push. In each case, the classical description declares a route inaccessible because an ordinary trajectory cannot cross the relevant energy barrier. The quantum state is not restricted in the same way. Its amplitude can extend into classically forbidden regions of the relevant space of possibilities. Sometimes that amplitude is extraordinarily tiny. Sometimes it becomes large enough to dominate an important physical process, and sometimes interference, resonance, or collective coherence makes the result far richer than the simple textbook barrier would suggest. But the rectangular barrier remains the clearest place to return. Imagine the particle approaching from one side. Its energy lies below the barrier height. The wave function reaches the boundary. Inside the barrier, it changes into an exponentially decaying form. If the barrier is narrow enough, some amplitude survives to the far side. That remaining amplitude connects to a transmitted state. A later measurement can then detect the particle beyond the region that classical mechanics called forbidden. Nothing in that description requires quantum mechanics to break its own rules. Quite the opposite. Tunneling occurs because those rules are followed. The effect seems impossible only when a quantum particle is forced into the classical picture of a tiny object travelling along one definite path with one definite kinetic energy at every point. Once the quantum state is taken seriously, the mystery changes character. The barrier is still real, the suppression is still real, The probability may be extremely small, but absolutely forbidden and classically forbidden are not the same thing. Quantum tunneling is not a loophole in quantum mechanics. It is one of the clearest demonstrations of what quantum mechanics actually means. So why can a quantum particle pass through a barrier it should never be able to cross? Because in quantum mechanics, the particle is not described only as a tiny object following one definite classical path. It is described by a quantum wave function, and that wave function can extend into regions that classical physics declares forbidden. Classically, the answer is simple. If a particle does not possess enough energy to climb over a potential barrier, it reaches a turning point and reflects. There is no chance of transmission. The probability is exactly zero. Quantum mechanics replaces that certainty with something stranger. Louis Victor de Broglie introduced the idea that matter possesses wave-like properties. Erwin Rudolf Joseph Alexander Schrödinger developed wave mechanics to describe how those quantum states evolve. Max Born then connected the wave function to probability, showing how its squared magnitude determines the likelihood of different measurement outcomes. When a quantum wave function reaches a finite barrier, it does not usually vanish at the boundary. Inside the classically forbidden region, it changes form and decays exponentially. If the barrier is narrow enough, some of that amplitude can survive all the way to the far side. That surviving amplitude creates a non-zero probability that the particle will eventually be detected beyond the barrier. How likely that is depends strongly on the details. Wider barriers suppress tunneling dramatically. Higher barriers do the same. A particle with energy closer to the barrier height generally tunnels more readily, while greater particle mass usually reduces the probability. That is why electrons can tunnel across distances measured in fractions of a nanometer, while the idea of an entire human passing through a wall remains. For every practical purpose, impossible, and none of this requires the particle to borrow energy. It does not briefly violate conservation of energy, find a hidden crack, or receive a mysterious push from somewhere else. The barrier remains higher than the particle's energy. What fails is not energy conservation, but the classical assumption that the particle must cross by following one ordinary continuous trajectory. The evidence for tunneling is everywhere. It helps explain alpha decay from unstable atomic nuclei. It allows charged nuclei inside stars to penetrate the Coulomb barrier and contribute to nuclear fusion. Scanning tunneling microscopes use it to probe surfaces at atomic scales. Tunnel diodes, semiconductor devices, and Josephson junctions rely on closely related quantum behavior. Even some chemical reactions involving electrons or light nuclei can be influenced by tunneling. There are still subtle questions. Exactly what path a tunneling particle takes depends partly on how quantum mechanics is interpreted. Exactly how long tunneling takes depends on how the time is defined and measured. But those deeper questions do not weaken the phenomenon itself. The transmission probabilities are calculable, the experiments agree with them, the technology works. The barrier only seemed absolutely impassable because classical intuition imagined the particle as a tiny object that had to travel through space in one familiar way. Quantum mechanics describes something more subtle, a state whose possibilities can reach into places that classical physics calls forbidden. And sometimes just a little of that possibility reaches the other side.